Thank you, Benno. All right, our second to last speaker today is Dan Crosta, who comes to us from New York, where he organizes Pi Gotham. I was out there this year, just last month. It's a wonderful event. You should go if you're ever on that side of the country. Today he's going to tell us about hypothesis and letting the computer write the tests. Please give him a warm round of applause.
Great, thanks, Sam. How do you know if you've written enough tests? Well, let me tell you, you definitely haven't. So I'm not talking about tests for catastrophic failures. I'm not talking about tests that sort of prove that your program basically works the way it's supposed to. I'm talking about tests that would catch small deviations from the expected behavior, the sort of thing that might be triggered by running in a slightly different environment than you expected, or user input that's mildly out of the ordinary. These are, of course, bugs that we can catch with more tests, but sadly, still for most of us, testing is an afterthought and often falls victim to tight schedules and other pressures on our time. As a result, we end up with fewer tests and more of these little bugs. So today I'm here to tell you about Hypothesis, which is a library that can help you write an order of magnitude more tests effectively than you have to write by hand by sort of generating inputs for your tests for you. Hypothesis is a property testing library. So property testing, or rather Hypothesis is relatively new. Its 1.0 release came out in 2015, so just a couple of years ago. But property testing itself has a bit longer of a history and seems to have hit its stride in the late 90s with a library called QuickCheck, which was a Haskell property testing library. Similar libraries exist for other languages, as you would expect. What all the property testing libraries have in common, though, is that they help you separate the structure of your test, so what you're calling and what you expect about its output, from the inputs that you're feeding into it. So in essence, you as the programmer control the program, but the users of your program control what inputs it gets. Property testing replicates this dichotomy in your test suite, and therefore sort of more accurately reflects the real world. Property testing is called property testing because rather than specifying particular inputs for your code, you specify properties of the inputs. So rather than saying call my function with the specific integer 1, you can say call my function with integers in general. So when is property testing appropriate? Basically any test can be adapted to use hypothesis and property testing. Most functions, most of our code either produces some output or affects observable state in some predictable and constrained way. And it's these constraints that we're looking to test when we're using a library like Hypothesis. So once we hand control of the inputs over to Hypothesis, though, we have to make our assertions a little bit more general. So in the example that I'm showing here, I hope that most of us are capable of computing the average of a list of 10 numbers. In this particular case, the answer is 4.5. But when we hand control of the inputs over to Hypothesis, we won't know what the specific inputs are, so it won't always be equal to 4.5. So in this case, we have to make our assertion a little bit more general, and here we can claim only that the average is going to be between the minimum and the maximum elements of that list. Another case where property testing can help us a lot is when we have paired encode and decode functions, or really any functions which are the inverse of each other. So this would have the property where I feed a value into one, and I take the result of that and feed it into the other function, and I should get back something that's equal to what I started with. Property testing can help us here by trying a much larger variety of values than we would have thought to write by hand, and it can help us uncover subtle bugs in the encoder or the decoder as a result. Finally, sometimes there's not really anything very strong that we can say about the code other than that it shouldn't fail, and these two are also great tests for hypothesis and property testing. So. In fact, this is basically a very hard test to write without property testing because by the time you've written the test, you know that it no longer fails, so you're not really learning anything new about your code from the test. With Hypothesis, when we give control over the inputs back to the computer, then we'll actually learn something useful about it because it's trying a much wider variety. Okay, so let's look at what testing with Hypothesis actually looks like. We're going to work through an example of converting a static test by first factoring its inputs, rather the inputs to the code under test, out of the test function itself and into parameters of the test where we can then give control of them over to Hypothesis. Once that's done, Hypothesis will be able to run our test multiple times with different inputs each time, effectively multiplying the number of tests that we actually have. So I work at Dropbox, I work on video at Dropbox, and this code is sort of very, very loosely based on some stuff that I was working with recently. One of the things with video that we have to deal with is video rotation. So on your smartphone, for instance, if you take video in the portrait mode, the sort of vertical mode, your phone's not actually recording video with those dimensions. It's actually recording effectively widescreen landscape video and just saving a bit of metadata that says your phone was rotated by 90 degrees. So we have some code that has to deal with that, and what it does is it looks for that metadata and it says, if it's rotated by a quarter of turn, then we're gonna swap the width and the height, otherwise we'll return them as they are. So here's the function that we're gonna be testing. The sort of main part of the body here, the bigger part of the if-else, is the guts of what we wanna test. So here's where it's actually looking at the rotation, checking if it's 90 or 270, which is rotated left or right, or maybe right or left. And then it's going to take a look at that and return either the height and width or the width and the height, depending on what the value is. Fortunately, we already have a test for this function. This looks like a basically kind of reasonable test. It's definitely not exercising all the different quartering cases that we saw by looking at that function, but it's a good starting point, and we'll incrementally build it towards something that's better using Hypothesis. So as I said, the first step is to factor the values out of the test. So where we previously had constants just in the test body, we've now used names and put those names as parameters to the function. And we've added this sort of extra decorator on top, which is basically what the hypothesis test actually looks like. So this decorator called given sort of marks this as a hypothesis test. And each of the arguments to that decorator describes how hypothesis should generate values for the corresponding arguments of our function. So those techniques are called strategies. That's the name that hypothesis gives to these things. And the real power of strategies and hypothesis is when we actually ask it to generate sort of random things. But just going step by step here for the sake of learning, we're using a strategy called just, which always produces, no matter how many times you ask it, it always produces whatever the one value is that we've configured it with here. Hypothesis has many strategies that produce all different types of things, so all the Python primitives, integers and floats, text and binary strings of various forms. It has strategies to produce containers, so you can say lists of integers or dictionaries keyed by text whose value is floats. There's a lot of power there. But in addition, and we'll see this in a couple of minutes, Hypothesis gives us tools to combine these to generate custom objects within our domain model, which turns out to be a really powerful technique that we're gonna wanna leverage. So returning once more to this test, one thing that's worth noting already is that we've already improved the test, even though we haven't actually sort of taken advantage of the major power of Hypothesis yet. By giving all of the constants here that used to just be numbers, by giving those things names, we've now made the test more readable. So it's a little more obvious that what this is doing is actually rotating the video because we're returning height and width rather than the more customary width and height. So if we were to run this test at this point, because we haven't actually changed anything really about what's going on, we should expect this test to pass. It's basically still a static test, it's just being run with Hypothesis. And basically when we run it, that's exactly what will happen. So let's start to take advantage of what Hypothesis has to offer. So we saw before that Hypothesis has a built-in strategy for generating text strings, and we know that this medium field is some sort of a text string. So let's go ahead and use the text strategy to try and generate values here. If you remember from looking at the code, we know also that the medium field only actually has two values that it'll accept. There's an assert right at the beginning that says it must be audio or video. So we expect this to fail, but let's just confirm that, and indeed, it does fail. This is what a failing hypothesis test looks like. So in addition to the traceback that you'd normally get from your test runner, you get this line at the end that says falsifying example, and then it lists the actual values that it used. This is really nice. I wish that all of my tests would tell me exactly what was going on when they failed. It's one of the other benefits of using Hypothesis is that you just get more insight into what's actually going on. However, we don't want our test to fail. So we can't just pass it any old text. Instead, what we're going to do is use a strategy called sampled from, which will pass it either audio or video, depending on sort of which one Hypothesis randomly chooses as it runs the test. So I think now that this test should probably pass, but it doesn't. So if you were paying close attention, this won't surprise you, but as I was preparing the slides for this talk, it surprised me. And it turns out that what's going on is there's a bit of the code there that I had sort of forgotten about, which is if the medium is audio, then it returns none rather than trying to rotate it. It doesn't really make sense to rotate an audio file. Audio files don't have a width and a height. So this is good expected behavior of the function. But we're already sort of learning more about our code base by using Hypothesis. So we can update the test to account for this. So now our test is actually proving more than it used to, because Hypothesis prompted us to do this. So what we're saying is, if the medium is audio, we're claiming always and forever that the output should be none. Otherwise, we have the same assertion as we had before. Next, let's replace the just strategies for width and height using the built-in integers strategy. So integers here we can sort of learn from our mistake the last time around, and we'll parameterize this right away. And we'll say that width and height must always be at least 1. We know that 0 will cause it to fail, because we remember that assertion, and it doesn't really make sense to have a negative width and height. So we're just going to say 1 is the smallest value that it can take, and anything bigger than that is fine. Remember that thing about 0, though. We'll come back to that in a minute. There's some potentially valid inputs that we're excluding here, and we want to make sure that we test those eventually. So we'll come back to that. Finally, let's take a look at rotation. So rotation, in order to pass this test, has to be a multiple of 90. There's no parameter that we can give to the built-in strategy to say, only give me integers that are a multiple of 90, but fortunately, Hypothesis has this thing called map, which we can use to transform the values of strategies after they're produced, but before they get fed into the test. So here we're just transforming by multiplying everything by 90, which by definition makes it a multiple of 90, so it should cause our test to pass. Indeed it does. Okay, so far we've been using the built-in Hypothesis strategies to generate values. Wow. Is everyone all right up there? We've been using the built-in Hypothesis strategies to generate values, but we've had to kind of customize them a lot to get values that make sense within our problem domain. So we had to multiply things by 90, we had to truncate certain things, we had to limit strings to just a certain number of values. What we can do instead, or rather next we're going to look at several ways that we can build our own strategies, both for sort of simple primitive types as well as custom objects that maintain the power and convenience of Hypothesis, but with which we have to be a little bit less verbose as we're sort of describing what a particular test can take. We'll do this by implementing our own custom strategies. So the simplest custom strategy that we can come up with is basically just renaming one of the things that we've already got. So here, we used to have directly in the given decorator an invocation of the sampled from strategy. Now what we've done is we've just wrapped that up in a function that we're calling mediums. Because it's just returning the strategy, it's exactly equivalent to what we had before, just sort of one level indirected. But again, by giving things a name, we're sort of improving the readability of our tests. So we no longer have to sort of reason about what things are or aren't valid when looking at the test. We can just assume that the strategy that we have that produces mediums for these media metadata objects is producing the valid set of things that we want it to produce. Of course, we can do the same thing for size and rotation. Literally exactly the same thing, just replacing the invocation of the built-in strategies with our custom functions that return the same thing. So our given decorator is still a bit wordy. We'd like to express our tests in terms of the object that the function we're testing actually takes, which in our case is this media metadata object. Unfortunately, Hypothesis gives us a way to do this. So there is a strategy called builds, which takes as its first argument a callable, so a Python class or a factory function or something of that sort, and then several other arguments, all of which have to be Hypothesis strategies. And every time we produce a value with this strategy, what it actually will output is the result of that callable called on the arguments pulled from those other strategies. So it's a little bit hard to see, but basically every time we pull from this strategy, we're going to get back a media metadata object given this medium, rotation, and width and height. We modify the test case slightly, so now it only takes one argument rather than 4. And we have to sort of use attribute access rather than directly accessing the variables, but it's basically a pretty straightforward transformation. So using this strategy, we know that we're going to produce media metadata objects that cause our test to pass because we've been using the same set of potential values that come out of these strategies before. We've just moved the instantiation of this class out of the test. But we're still kind of lying a little bit. So the docstring here says that we're generating valid and plausible media metadata objects. However, when we happen to pick audio as the medium, we're going to be still generating a positive width and height, and we have a 75% chance of generating a non-zero rotation for the media metadata. So again, this doesn't cause our particular test to fail, because our particular test just doesn't have any behavior that cares about these things. But now that we've given this thing a name, and we might be using it for more places within our code base or within our test code base, some of those other locations might be more picky, and they might have failures, spurious failures, because they are expecting it to conform more truly to sort of the actual valid cases that would exist in the wild. So the build strategy that we've been using is appropriate when values in an object don't depend on one another, or if you don't care about that dependency, I suppose. But there's, again, a more powerful approach that will give us even finer grained control over the things that go into our object. That's called composite. So a composite strategy is a Python function or a Python callable that's wrapped with the composite decorator. And what that does is it passes a single argument to our function called draw. Draw lets us programmatically, interactively get values from any number of other strategies. We don't have to sort of inform hypothesis about those strategies. It doesn't need to know about them ahead of time. All we need to do is just have access to them, and we can call draw on those strategies, and we'll get values out. So in this particular case, the way that we're going to make our media metadata valid is by first drawing the medium, and then if that's video, we will also draw rotation, width, and height. Otherwise, we'll set the rotation, width, and height just statically to 0, and then use the result of all of those draws or not draws to actually instantiate the media metadata object. We can take this even a step further, and we can have separate strategies for producing audio metadata objects and video metadata objects. What's nice about this is that it makes it a bit clearer that there's really only one valid audio metadata object, because we're using just there, so it's the one that has zeros for all those fields. But there's potentially infinite number of different valid video metadata objects, because they can have any width or height and any video rotation, because we haven't sort of capped it to any particular value. However, our test still needs to have both, right? Because we have test cases that test both audio and video. So we have this media metadata object that just, again, combines those two strategies together using one of, so it basically will pick one or the other each time you draw from that strategy. Cool. As powerful as hypothesis is, we can't just replace all of our testing with hypothesis, or at least I don't recommend that you do that. We've been really careful so far to make sure that what we're generating are valid inputs that actually happen to cause our test to pass. And we did this from a good place, right? We're not lying to ourselves. What we're really interested in doing is making sure that across all the spectrum of things that we do consider to be valid, that our code behaves correctly. But it's equally important to make sure that we behave correctly when we get some invalid inputs. So let's look at how we can do that next. Unfortunately, there's no way to just take the inverse of a strategy with hypothesis. It would be really nice if there were, but the way that we define these things, because they can be custom code, hypothesis doesn't have enough semantic information to figure out what the inverse of that ought to be. So instead, we'll use the same approach as before, and we can just define strategies and parameterize them in such a way that we know that they generate things which we consider to be invalid. So for example, here for medium, we can take any text other than audio or video, because those are the two things we consider to be valid. Likewise, for rotation, we can take any integer at all, unless it's a multiple of 90, in which case we don't want it because that would be valid. All the same techniques we just looked at for defining custom strategies and giving these things names, of course that all should apply here. I just didn't want to take up a lot of time in slides going through what all that looks like, because we just looked at it. When there are particular test cases that you want to run, let's say the username of the CEO, or some other high-value input that you want to make sure gets tested every time, you can use the example decorator to force hypothesis to run the test with the values that you specify in it. You can specify example multiple times, and whatever examples you give using this decorator will get run before any of the random ones do. Because you're asking hypothesis, you're saying these are really important things, so it's going to test those first and report any failures it finds there before any sort of new random ones that it happens to come up with. Examples also a tool that you can use when you have some behavior that is very unlikely. So here we have some behavior that depends on a particular integer out of the whole world of integers. It's very unlikely that hypothesis will pick that one in particular. So we can use example to force it to do that if we know that that exists. The sort of inverse of example, we saw filter before, but there's also a helper called assume, which we can use to say basically if hypothesis happens to pick this number, just don't run the test, just skip it, and it'll come up with a new random sample the next time it tries to run this test. And then finally, we looked earlier at how we kind of generalize our assertions when using hypothesis. For many things, probably almost for everything, we actually want to have at least one test that makes sure that it does specifically what we want. So if we wrote a function that computes the average of a list, somewhere there needs to be a test that makes sure that it actually gives you the average of that list and not some other number. I hope this isn't controversial. Now, you may have wondered why the failures that we've seen coming out of hypothesis have happened to have the particular values like 0 and the empty string, and simple examples like that. Why, out of all the possible random numbers that we can come up with, why does hypothesis test those? Does it test them first? So no, hypothesis uses a technique called shrinking to give us failing values in the error message that are easier for a human to understand. So after a hypothesis finds a failure, it applies shrinking to the values that caused failure sort of repeatedly and makes sure that the test continues to fail while shrinking the value each time, say, towards 0 for numbers or towards the empty string for strings. And understanding shrinking is also a really great way to look at how a hypothesis generates test data in the first place, which I think is really interesting. So hypothesis is a really big library, and I don't have time left to sort of trace through all of the things that have to happen in order to generate test data. So this is a gloss. This is not sort of what hypothesis actually does, but it's approximately correct, and it'll give you the right intuition for thinking about what hypothesis is doing under the hood. So each test example that a hypothesis runs, it generates a big blob of random data. This defaults to 8K, but you can actually set how big that is. And then uses that to feed into all of the strategies. So the strategies will each get sort of a portion of that data set assigned to them, and then they're responsible for interpreting those random bytes into a value of the type that you've asked for. So here, for instance, suppose that we were writing the integer strategy. We could use struct.unpack to create I think this is a long int out of 8 bytes of random data. Once again, I want to just say, I think this is probably not actually what hypothesis is doing under the hood literally, so please don't come after me with a pitchfork if you're an author of hypothesis and you know that this is wrong. But notionally, it's sort of going in the right direction. Okay, so let's say that we ran our test case with this example and it happened to fail. So what hypothesis could do is it could say, your test failed when we gave it 8 quintillion, 813 quadrillion, 743 trillion, 250 billion, 675 million, 301,270. But that's a really big number, and it's not one that we can reason about very well. So instead, what hypothesis does is it sort of progressively zeroes out parts of that random data. Like literally, it just replaces them with 0, and then reapplies the interpretation back to an integer to it. And as you can see, as I replace progressively longer and longer prefixes of this random string with zeros, I get numbers that are smaller and smaller. There's a little bit of interaction that the code for each strategy can do to sort of hint hypothesis how to zero things out. And sometimes they can override things too. So like the shrinking strategy for integers says it will always try as a potential shrink whatever the value was last time -1 and -2. Again, the details of that sort of is up to each strategy, but broadly speaking, this is what it's doing. Because hypothesis has shrinkers for all of the built-in types for all of the base strategies, that also means that our custom strategies, which are just built on composition of those base strategies, also get shrinking for free. And this is why we've seen examples where the failure cases were very small. So I asked hypothesis to run a test, and I sort of caused that test to fail, and I asked it to tell me all the values that it was trying along the way, and I happened to get this. So just looking at the rotation field here, you can see that it starts off as some very big negative number that I won't try to read, but progressively shrinks down until it gets to 1. And we know, because we've looked at the code, that 1 is not a valid rotation because it's not a multiple of 90. So that's much easier to see with a small example why it's failing than with that very big example. All right, a few other things I want to mention before we go. So I just showed you a trace of what hypothesis is doing under the hood. You can do that yourself. There's a settings decorator that you can put on each test, and you can give it, among other things, a verbosity setting, which will cause it to print that out. There are settings for timing, for the number of examples it should run, for setting the random seed, for de-randomizing hypothesis, so it'll still pick values that are different each time, but it'll do it deterministically. That's probably mostly useful if you're just working on a strategy rather than writing tests using one. You can also, if you're using PyTest, you can register profiles of different settings in your conftest.py file. And then use those, or rather select one at the command line if you install the hypothesis PyTest plugin. So, as we've seen, property testing with hypothesis is an effective way to gain more confidence that your code is behaving properly, meaning the way that you want it to. Because it doesn't rely on fixed values, it's not subject to the assumptions that you, the programmer, had when you were writing the code to begin with. Because of this, property test with hypothesis better simulate the real world and find more bugs. Hypothesis also encourages better practice in both testing and coding. So because each test is run dozens or hundreds of times, you'll find that as you start to use hypothesis, you start to write tests that are each smaller and more focused and faster, importantly. And because it focuses your attention on formulating inputs to your code, you'll start to think more about what should the interface to my function actually be, rather than just sort of accepting whatever happened to be convenient the first time you needed to use it. So in short, I claim that property testing makes both the code and the coder better, and that adding hypothesis to your project is a straightforward and high leverage way to improve its quality. Thank you, and please remember to vote on Tuesday.
Thanks, Dan. On behalf of the organizing team, here is one of our wonderful designed in Petaluma Camelback water bottles. Everybody, please thank Dan Crosta once more. Yeah, come plug in, Steve.